So this next video is Mr. G calls it using confidence intervals wisely. Basically, it just sets the stage for what are the conditions that we need to check to make sure that our data fits into the right model so that the confidence interval that we create would be valid. So using confidence intervals wisely, in other words, what conditions will be necessary, and we will talk specifics in sections 8.2 and 8.3 when we're talking about proportions and means. These conditions are going to have to be checked every single time, and so you're going to hear this a lot, but get these things locked in. Okay, here are the conditions, and they're going to be these or variations on them almost every time. Number one, was the data collected randomly, right? Be sure your sample was randomly selected, an SRS, or randomly assigned to treatments and experiment. The fact is, we're going to be reading about someone else's work, so you're not going to be designing it. You're going to have to say, hey, it was stated that it was random. This is legit, right? If it doesn't say in there that it was random, you need to write this or some variation of it. Sample was not known to be random. We will proceed with caution, right? See a lot of kids lose points on, like, when I'm at Nerd Camp grading AP exams, one of the things that people forget is to acknowledge that randomness. Either, yes, it was stated to be random, or, ooh, I don't know, so I'm suspicious here. I'm proceeding with caution. It will be stated in the problem. If it's not stated, this is how we get around that. In real life, you're designing the experiment or the sample, so of course you're going to do it randomly. But this is our check. The second part is independence, right? The independence is what gives us the permission to use the standard deviation formulas that have become hopefully pretty familiar now. If we're talking about means, this is going to be 7.3. The standard deviation of all the x bars that could possibly happen, the standard deviation from the whole population divided by the square root of the sample size, or if we're in section 8.2, which is about proportions, the standard deviation of all the p hats that could occur is the square root of p times 1 minus p divided by the sample size. Okay, those are the formulas. It's the 10% condition. Now, here's what I need to point out. Mr. G says the population is 10 times the sample. Darren and I say the sample is 1/10 of the population. Hopefully that makes sense to you. It's the same thing. 10 times the sample size makes the population, or it's larger, or the sample size itself is less than or equal to 10% of the population, right? If this isn't met, here's something that he includes. I've mentioned it before in class one time. I know at least once. It can still be done. It's just not done in AP statistics. There's this little thing here, which is the same thing over here. It's called the finite population correction, FPC. That's what you can use if we don't meet the 10% condition. But you know what? You can completely tune that out because that is not part of the AP Stat curriculum. And so you can ignore it. But I want you to be aware it does exist. We're not stuck every time we can't meet the 10% condition. It's just that we've got to do some extra stuff. And for whatever reason, Darren and the rest of the brain wizards decided we're not going to include that in AP Stat. So whatever. It's just it's for your own awareness. The final condition that needs to be met every time before we can do this stuff is we have to have a normal distribution. The sampling distribution has to be approximately normal. If it's not approximately normal, we can't do anything with it, right? So if we're talking about proportions, right, this will be 8.2. If we're talking about p's and p hats, n times p and n times 1 minus p both have to be bigger than or equal to 10, right? Same check as it was back in 7.2 for proportions. For normality, for proportions, n times p and n times 1 minus p, both greater than or equal to 10. Note, central limit theorem does not apply with proportions. It doesn't make any difference. That doesn't work. It's not something that we can use. The central limit theorem is out the window when we're talking about proportions. But when we're talking about means, okay, this is what's going to be in 8.3. It was just like it was in 7.3 when we're talking about x bars and mu's, right? We can't do n times p and n times 1 minus p because that doesn't make any sense. We've got two different things, and this is a big old or. If the population itself is normal, we're golden, right? We can proceed right on through. Our sampling distribution is going to be approximately normal. If the population is not stated to be normal, the other trick that we've got to show normality for sample means, it's this thing called the central limit theorem. If the sample size is large enough, 25 to 30, 30 is what Darren and the gurus say. 25 actually pretty much works. So 25 or 30. If our sample size, if little n is 30 or more, we just say central limit theorem, the sampling distribution will be approximately normal, and we can rock and roll with means, right? For means, if the population is normal or the central limit theorem, either one of those two things, and we know that our sampling distribution will be approximately normal. Those are your conditions, those three things: randomness, normality, and independence. Independence, 10% condition. Randomness will have to be stated. Normality, n times p and n times 1 minus p, or central limit theorem or population normal, right? Depending if you're in means or proportions. Have those on your notes or whatever, but those are going to be the things that you're going to need to have. What if it's not normal? Then we say, hey, we can't do this, right? If it's not normal, if you can't check n times p and n times 1 minus p, or the central limit theorem, if you can't check for normality, if you can't prove normality, we can't do norm CDF, right? There's no way that we can do this, right? These are the ones that you would love to come across and say, sorry, I can't do this. Of course, in this course, there are going to be ones that you can do. But if it wasn't, you could have a question that says like, hey, could this be calculated? Why or why not? And you would say, oh, no, it can't, because we don't know if the sampling distribution is approximately normal. Okay? Randomness, normality, and independence. If you have those three conditions, we're going to be good for doing our confidence intervals. We will talk about the specifics of confidence intervals in 8.2 and 8.3 beginning next week. But these 4 days this week are about what the heck is a confidence interval.